Okay, so we're going to talk about vertical motion now, and vertical motion, we've been talking basically horizontal motion like cars on the road going around circles, but now what we're going to take a look at is what we have is a bucket of water rolled in a circle. Now, I am trying to do this with my mouse. I did not bring Moby home, so this is not going to look pretty, but hopefully you'll get the idea. And I'm going to whirl it around, and it'll be on the top of the vertical motion. It'll be at the bottom of the vertical motion. Wow. And I just want to draw a free body diagram because obviously I can find F sub c. This is my mass, v squared over r, and we can certainly get an F sub c. Now, what's more important here is what's going on with the free body diagram. So I have F sub g is down, of course, and at the top or the bottom. But what's interesting is that the normal force, or what we're going to call the tension force, but this can be used as a roller coaster problem too, so I'm going to talk about it as a normal force, but it's also the tension force in the rope. You can kind of think about it as the tension if you're swinging around. In class, I'd have you actually do this and swing it around like so, and you'd feel the tension upward on this. But let's talk about it as a roller coaster type thing because the two are going to be identical. We might call them different forces, but it's the same idea. Now here though, as it goes around, let's say that we had it right here, we'd have F sub n like so, or the tension like so, toward the center as it goes around like so. So what happens up here is that this is supposed to be another straight line, our F sub n goes down. Now, from a centripetal force requirement, centripetal force is always, that is supposed to be straight down, people. Centripetal force is always toward the center. So, oh my God, what's happening here is F sub c is toward the center. Okay, so here at the top, what's happening is F sub c is provided by both F sub g and F sub n. So what I would say is F sub c equals F sub g plus F sub n. And over here, what we see here in the free body diagram, and I can't stress how helpful free body diagrams are in solving any type of Newtonian physics problem, we have F sub n toward the center, but F sub g is actually directly away from the center, so it's minus F sub g. All right, so hopefully that makes sense from a free body diagram experience. Now, what's also interesting here is what is felt, and if this were tension, if I put tension in here, or if this were a roller coaster, I have F sub n, it's the same thing. What is felt is on top, it feels lighter. Just think about swinging something around like that. And at the bottom, it feels heavier. On a roller coaster or a fighter pilot or something like that, we call this negative g's. It's really just like a fraction of a g. But here, we call these extra g's. And that heaviness, those g's, really can't top more than, like 5, 6 g's before it really gets difficult to handle. Up to about 10 G's, it kind of depends, but 10 G's definitely pass out or possibly die. Okay, so why am I telling you that? Because often what we want to do is isolate what we're feeling to calculate the G's. So here what we'd have is F sub n is F sub c minus F sub g. So you can see why you get the smaller number. And over here, this is what you want to focus in on. And over here, F sub n is going to equal F sub c plus F sub g. Oh, gosh, I wish I brought the pointer home. Okay. All right, so here at the bottom, you can see you're going to get mv squared over r plus mg. You're going to have a feeling that is greater than just F sub g. All right, so I could plug all all these numbers in, but let's go ahead and look at the next slide here. Roller coasters used to be made in perfect circles, but again, if you think about that in what we talked about in the last slide, you really can cause some real problems at the bottom going too fast because you get so much F sub G and F sub N, but at the top, if you slow it down, you might not make it around. So they invented this clothoid loop where you would have a smaller radius on top and could make it around with a low speed, but you could enter at a high speed and not, have anyone get hurt. All right, so looking at our formulas here, if I have a 1,000 kilogram car, and by the way, we could talk about this as a person in the car too. We could say a 50 kilogram person in the car and focusing on the person rather than the car. So either way you want to do it, but let's talk about the car. So what is this feeling here? Well, this feeling is going to be F sub N is going to equal F sub C. Now, F sub C is going to be this mass times this acceleration at the top. They already put v squared over r in there. And what we're going to do is say, well, this is 1,000 times 15 meters per second squared. So we end up with 15,000 newtons, okay, minus F sub G, which is going to be 1,000 times 9.8. So, wow, this is so hard to do with the mouse. Alrighty, I may just talk about this at this point. Okay, so I'm taking my F sub C, which is 1,000 times my acceleration, and I'm going to subtract 9,800. All right, so 5,200 newtons of normal force. Okay. So that's the net force. That's the feeling. And they're inside the loop. We should talk about what if it's, kind of going over a hill too, because, well, we'll talk about that in the next slide. I think there's one. But let's talk about what that means. How does 5,200 compare to how a person would be feeling just sitting on Earth? If this car, we're going to talk about in the terms of the car versus the person, but again, we could do this all substituting in the mass for the person. And okay, so this is going to be 0.53. So you're going to feel weightless. You're not going to feel your full 1G. But now here, what's going to happen, I'm not going to try to rewrite this, but I'm going to add this. So this is going to be 15,000 plus F sub N at the bottom is going to be plus that. So the feeling is going to be 15,000 plus 9,800. We're looking at 24,800. Now compare that to what you'd feel on the ground. So let's go ahead and divide that by just the 9,800 to see what's happening. Oh my goodness. All right. And compared to the 9,800 you'd feel, we're looking at about 2.53 Gs. And that would be probably about the max that a roller coaster would want to do it. Okay. All right, so in this particular one, what's happening is you've got a car going over the track. It's going to be the same kind of thing that's happening here. It's going over the track. Now, I know as you're going over, you're probably thinking, okay, well, F sub N is upward. And please note, because this does get a little interesting, if I had a motorcycle and I'm going over the hill, right, flying over this pretty steep hill, F sub G is down. And you are right. If I just was sitting on this motorcycle, just sitting up on top of the hill, I don't know, looking over nature, That is true. That is what would happen. I mean, you draw the free body diagram just like that. Now, if you're flying over this at a speed, a certain speed, think about what would happen if gravity, F sub g, was not enough. That's a not equal sign. Not enough to provide the centripetal force. If gravity was not enough to provide that centripetal force, what would you do? You've seen this, I'm sure, in movies and stuff, ATV. You're going to go flying, right? You're going to lose contact with the ground. The F sub g was not enough to keep it in centripetal motion. F sub g would equal F sub c if you're going to stay contact with the ground. But if there's no contact with the ground, I think there's a homework problem about this too. If there's no contact with the ground, you go flying. So what if you're on a roller coaster? Now, if you're on a roller coaster, what's going to happen is they are going to hopefully hold you into place. And when they hold you into place, they're going to provide some extra F sub c in terms of an applied force. I'm going to just go ahead and call it a normal force because it's a contact force. I guess technically maybe you should call it an applied force. It's something that's holding the car on the track. It's a seat belt holding you into the car. And there have been many stories about people on roller coasters who haven't been belted in for whatever reason, and they do go flying. Okay, so we have to use the same, all that to say is use the same formula that you're going to be using for any of these, whether it be a fighter pilot, a roller coaster, a tension and a rope. You're going to, at the top of the hill, use, or top of the roller coaster, or top of the flight, whatever you're doing, you're going to use F sub n is equal to F sub c minus F sub g. At the bottom, you're going to use F sub n is equal to F sub c plus F sub g. Okay, so, and then you can always compare those numbers to what is just the actual F sub g to find how many g's that you have. So I cannot seem to write, but you guys can plug in numbers here. Like here we've got the mass v times v squared over r, and over here we've got the same car, 1,000 times 12 squared over 15. So either way you could calculate F sub c. F sub g is 1,000 times 9.8. At the top you're going to take F sub c minus F sub g. At the bottom F sub c plus F sub g. And that's going to give you this feeling or this normal force.